Let's take a look at this circuit. It's put together with an inductor, capacitor, and two resistors, and we have both a voltage source and a current source. What we know for this circuit is we know the frequency that it's operating. We know it's operating at 1200 radians per second. And we also know the current through the capacitor, and we know the current through the inductor. We don't know the current from this current source or the current from this voltage source, but we know they're sinusoidal sources, so we can use our phasor analysis. And we want to find the phasor current that represents the current source, the phasor voltage that represents the voltage source, and the time domain current through this resistor. So we can analyze this in frequency domain and then convert it back to time domain using our conversion of phasors. So since we know the frequency, and we know the inductances and capacitances, we can determine their impedances. So we'll look at it in terms of impedance. So we'll look at our capacitive impedance, 1 over j omega c, or negative j times 1 over omega c. And at 1200 radians per second, this 25 microfarad capacitor has a reactance of negative 100 over 3, or we could write that as 33.33, but we'll leave it as 100 over 3 ohms, and it's negative. Our inductive reactance is 1200 times 10 to the negative 2 for 10 millifarads, and we get our J 12 ohms. So 33.3, we see that the inductive reactance is about 3 times that of uh, the capacitive reactance is about 3 times that of the inductive reactance, but they are oriented in parallel. They're not in parallel, but their orientation is not in series, so we can't just sum them. So if we can just take this circuit and analyzing it at 1200 radians per second, we can put the exact impedance associated with the capacitor and the exact impedance associated with the inductor at the 1200 radians per second. So now we need to come up with a strategy to find the current phasor and the voltage phasor of our sources and this time domain current. Well, finding this current phasor, we could just sum together these two current phasors using a KCL, but we don't know this I-20 as it's labeled. But we could find it since we know the current through the capacitor and the capacitance, we can find the voltage across the capacitor, and it's in parallel with this resistor. So we could do that, and then we could find this current source, and then we could go over here and we could find IR plus, IR is equal to IS plus IL. So we know these two. So that's how we could find this current here. And then we could find our voltage using a KVL. So let's put together that strategy. Our strategy is to first do a KCL at this node up here on the right, and then it's basically still our Ohm's law, that's just a voltage phasor divided by 20 ohms to find the current through the 20 ohm resistor. And then we can only find that once we find that voltage. So we find that voltage using voltage across the capacitor is the current through the capacitor times its impedance. And then we do another KCL at the left node, and then we can do a KVL around this left loop here. So approaching that, we can plug in now what we have known. What we know then is the current through the capacitor. So that's plugged in here in blue to make it easy to see. And then we know, again, that current through the capacitor, we can plug it in our third equation here, and we need to find that. And we also know the current through the inductor, so we'll plug that in here and here. So then we can go ahead and approach this problem. The first thing we can find then is going to be, it's not our first equation, but it's the first thing that we can find is the voltage across the capacitor. So plugging that in just by multiplying the capacitor current by the capacitor impedance, we get 40 angle negative 62 volts. We might want to do 62 degrees. do a quick check here, and we do see that the current through the capacitor and the voltage across the capacitor, the difference there is 90 degrees. And in fact, we do see that the current through the capacitor is leading the voltage across the capacitor by 90 degrees. So that's a good check that we can do before we plug that in to our I-20 equation. Plugging it into our I-20 equation, we get that current through the 20 ohm resistor. So getting that current through the 20 ohm resistor, that was all easy because we were just dividing. And here we did, well, here we multiplied this. We could this is 100 over 3. That negative J, that's just negative 90 degrees. So we really only, we could, do the calculation quite easily, writing it out in our head. We could do it in our head. Well, if you can do 1.2 times 100 over 3 in your head and to come up with 40, right? All right, so that next thing then we'll plug it up here. So now what we need to add is this 2 angled negative 62 degrees to 1.2 angled 28 degrees. Again, easy to do in your calculator instead of having to go through the conversion to rectangular form, but if you plug that into your calculator, and we like to see our phasors for current and voltage in this phasor form where we have the magnitude and the angle. So plugging that in, we sum these two. We get that this source current, the sum of I-20 plus IC here is 2.322. Our angle is negative 31.04 degrees. Again, the magnitude of 20 versus this is our 33.3. We see the capacitive reactance portion is greater than the 20 ohms. However, they're in parallel here as this is dividing. So if we compare the voltage across this network and the current going into the network, we do see that the voltage is lagging by about 30 degrees here, about 31 degrees. So that lagging voltage due to the fact that it's going to be net capacitive. And so again, a good check always where the lagging and leading comes in. So now that we have our IS, we can plug in and find IR. We can find IR by plugging in for IS here. When we do that, we get the phasor current through this resistor. We're looking for the time domain current. Before we convert into that time domain current, we can first get the voltage due to our source. So the voltage due to our source, again, we have to multiply this current by the 10 ohms, right? So by that 10 ohms up there, and so this is going to be 39.86. Angle 17.42. We lost the degree sign, but that's a degree. And it's important to have that degree sign there because if it's not a degree sign, the SI unit is radian, and so that is in degrees. So now we can just go through and add this up, so we'll be able to solve this with these 5 equations, and very easily if we have our calculator that we can use properly in convert between polar and rectangular form. So we're pretty much done here with the exception that we need to find our current in time domain. So if we just look at what we have found so far, what we still need to find, we got our final solution here. We weren't really looking for V20 or I-20, so we didn't put a box around them, but we did underline them to make sure it was clear that they were important parts of our solution. The other thing we could do is number our equations. That's always a handy thing to be able to follow work, number our equations 1, 2, 3, 4, 5, but we came up with our strategy by starting to do a KCL at this node B and then working back on the KCL at node A. But we finally did have to do a KVL to get this voltage. So if we're going to convert this current back to time domain, we know the frequency, right? So our IR of T, I'm going to write it right above it, but it's going to be 3.986. We're working with cosines because that's the real part of our of our complex number using Euler's identity. We'll plug in for our frequency, that's 1200 radians per second, so it's 1200 T, and again, we better put our degree sign in there, and that's going to be plus 17.42 degrees amps. And so then we're all set. But finally, we can do a check because we have, from the perspective of this voltage source here, we could find from here what is the equivalent impedance looking in, right? That ZEQ, that's just equal to VS divided by IR, because IR is the source current here. And what we see is the voltage source is leading its current, by whatever that 74.55 minus 17.42 degrees. So from the perspective of this voltage source, what we have is a net inductive circuit. We also have that current source in there, but we do have a net inductive circuit because the voltage is leading the current. If we, again, when we look at this, we say, well, that's J12 ohms, and that's J33.3. There is more capacitive impedance in this circuit than there is inductive impedance. However, the orientation here is that this current is dividing. So even though they're not in parallel, that's as though they're in parallel. So the admittance is, so that has the effect of allowing more of this current to flow through the inductor because it has a smaller impedance than through this capacitor. So that's a good check for our understanding as well as once we have that as understanding, we can do it as a check to make sure that we got our right results.